So this video is a quick review of intermolecular forces that you would have seen last year in grade 11 chemistry. So you'll remember that the prefix inter means between. So in this case, we're talking about the forces of attraction that exist between molecules. So in this example, I have an HCl molecule and another adjacent HCl molecule from the same sample. And so if we kind of juxtapose or compare intramolecular forces, those forces that exist between atoms in a molecule, versus those that are existing between adjacent molecules, our intermolecular forces are quite weak in comparison to the intramolecular forces that we just spoke about in our previous video. And that's because, if you look at a covalent bond, you're looking at a bond that's keeping the structure of a molecule intact, right? And so, that has to be strong. Otherwise, we're dealing with, molecules of matter falling apart. Intermolecular forces, conversely, are quite weak and easier to break apart. Now, let's just say, for instance, substitute these two molecules with water molecules to give you a good example. If this was a water molecule and another water molecule, and we'd started to boil it, all we'd be doing is creating water vapor, right? But still water. We wouldn't be breaking apart the bonds between hydrogen and oxygen. We would be breaking apart those intermolecular forces. So if we compare the strength of the forces, covalent bonds, if we assign them a strength, and this is just like, frame of reference, this is just arbitrary. If we assigned a covalent bond about 100, then our intermolecular forces would be much smaller in magnitude compared to that. So that just gives you an idea about how much stronger, in fact, our intramolecular forces are compared to our intermolecular forces. And that's important. We don't want to just, be heating up water and suddenly end up with hydrogen and oxygen gas. And that's just one simple example. Okay, so to remind you, and before I go through these, maybe in your head or on paper, jot down if you remember any of the four types of intermolecular forces. The first is LDF forces, London dispersion forces. I'm going to talk about each of these in the next few slides. The next is dipole-dipole forces, hydrogen bonds, and finally ionic forces, which are not really intermolecular because ionic forces of attraction are sort of electrostatic. There's no sharing of an electron or electron pair. One electron is donated to another atom, and so we end up with ions. So collectively, we call the first three van der Waals forces. Those are the forces that work between molecules to hold matter together, samples of matter. So London dispersion forces, and again, this should all be review hopefully, but just to have you hear it again. So all molecules have LDFs, and that's because all molecules have momentary dipoles. So if you're a nonpolar molecule, then that's all you have. London dispersion forces are pretty weak, but this is basically how they work. I'm just going to scroll down to a picture here, and that'll help you understand. So I want you to imagine that you have particles with electrons moving around in their electron clouds. And so at any one moment in time, one particular atom's electrons might be on one side of that electron cloud, and that draws, therefore that probably repels the electrons in the adjacent atom, but also causes these two atoms to be attracted to each other because of their oppositely charged nucleus, right? So that doesn't last for any amount of time. It's called a momentary dipole because these electrons, of course, are going to be not stuck in space. They're going to be moving around all the time. And so if we're looking at what's going on in terms of a polarization view, we're going to end up with a slightly negative momentary dipole and therefore a slightly positive momentary dipole in an adjacent atom. Okay, and they're going to be attracted, but just for a second, it's momentary. So as you can imagine, because it's not lasting for any length of time, it's pretty darn weak. And so if you're a nonpolar molecule, that's all you have. I want to talk about this a little bit more. So, what we see, again, to reiterate, is that we see electrons on one side of that atom for just a kind of moment, and that attracts that, and therefore that atom is attracted to an adjacent atom's nucleus. And we could be talking about molecules here as well. And so what we need to talk about next is what happens if we have two molecules that are both nonpolar. How do we judge one atom's sort of polarity versus another? Let's look at that. So the strength of the LDFs are related to the number of electrons. And so, I'm going to go back to the previous slide to help out with this. But if we were to compare two organic molecules like ethane and hexane, well, I know that my ethane molecule has a certain number of electrons in it that are going to each create little momentary dipoles. But my hexane, because it's so much larger, is going to create so many more little momentary dipoles such that it will do a better job of attracting other adjacent hexane molecules towards it. And so I would say that even though both of these are nonpolar molecules, hexane, is better at attracting more of its own towards itself, more LDFs. So as a consequence of that, we see that hexane is actually a liquid at room temperature, whereas ethane is a gas at room temperature. And that's just a function of the number of LDFs. So larger molecules have more electrons and therefore will have stronger LDFs, stronger intermolecular forces, and therefore are going to be more attracted to each other. All right, so let me go back to the previous slide here. And so again, we're looking at so many more of these momentary dipoles in a larger molecule like hexane compared to what we would see in ethane. Okay, so next we have our dipole-dipole interaction. So I want to talk about this before we take a look at some of the writing. So when I look at this, and I analyze a molecule of HCl just like we did in the last video, we look at electronegativity differences and we can assign chlorine a slightly negative pole and hydrogen a slightly positive pole. Now those are not momentary dipoles, those are permanent dipoles because chlorine really likes to grab electrons and kind of hog them. So that's permanent, it's not momentary, it's going to be long lasting and therefore stronger. And so as a result of that, we have the chlorine's slightly negative pole of one HCl molecule attracted to the slightly positive pole in an adjacent HCl molecule, and specifically that hydrogen end. Okay, so that's what a dipole-dipole force is. So dipole to dipole. Okay, we see this when we start to look at polar molecules that have permanent dipoles based on when we look at the type of bond between those two atoms. So here's my example HCl, and we just talked about it. So opposing charges on neighboring molecules will attract those molecules together and create that force of attraction. Okay, so the strength of the dipole-dipole bond is related to the polarity of the molecule. So for instance, if I were to look at the size of the dipole vector that gets created within a molecule, and one substance has a greater net dipole than another, then that molecule is going to have stronger intermolecular forces of attraction. Okay. Okay, so lastly, we're going to talk about, hydrogen bonding. And so I want to talk about hydrogen bonding as it compares to dipole-dipole, because essentially they're just hydrogen bonding could be considered a subcategory of the dipole-dipole. The difference being in that hydrogen bonding happens with really, really small, highly electronegative atoms. Okay, so it's a special kind of dipole-dipole when hydrogen, which itself is very, very small, is bonded to very small, very electronegative atoms. So which atoms on our periodic table are really, really small and highly electronegative? Nitrogen, oxygen, and fluorine. So when these molecules are bonded to hydrogen, we create molecules that are very, very small and therefore can kind of get jam-packed closer together. So one way to think about this is to think about it sort of like magnets. If you have magnets with opposite poles, the closer you draw those two different magnets together, the stronger you feel that force of attraction. So if molecules can get closer together, they're going to feel, that force of attraction, more closely. All right, so now that makes that stronger force of attraction. And again, as I just said, those particles can get closer together and therefore create a stronger intermolecular force. Okay, now lastly, we have our ionic bonds. So now ionic bonds are not really bonds in the sense of like covalent bond and sharing. In the case of ionic compounds, we have one atom in the compound donating an electron to the other so that both of them become more stable. And so now if we have ions of opposite charge, they're going to be attracted to each other electrostatically. Now that creates what we call a crystal lattice, okay? And so a crystal lattice is just a three-dimensional arrangement of ions. They can be atoms as well, but in the case of ionic crystals, it's ions. And they have what we repeating subunits, and that repeating subunit is sometimes referred to as a unit cell. So I've highlighted the unit cell in this compound, which is LiCl. So ionic forces are super, super strong because as you can imagine, I've got a complete positive charge and then a complete negative charge. They're going to be electrostatically attracted to each other and create a really, really strong compound. Okay, so I think that's about it. So we've talked about intermolecular forces. Now let's just do a quick review of which ones are the weakest, which ones are the strongest. I want you to think in your brain about if I had to arrange these from weakest to strongest, how would I do it? I'm hoping that you would place London dispersion as the very weakest because molecules that are nonpolar only have those, and nonpolar molecules are weakly attracted to each other. Dipole-dipole's next. Hydrogen is really just a subset of dipole-dipole. It's a little bit stronger. And then we have ionic at the top end. But of course, these are just generalizations, and we'd have to really look at individual scenarios. I hope that this was mostly a review for you and that when you see the practice questions in class tomorrow, you'll be able to navigate them.